Hello, everyone. So this is the lecture on section 3.7 on rational functions. Actually, I'll probably, this is a long section, so I'll probably split it up into two parts. So this is part A, the first part. So 3.7 on rational functions. Okay, so the first thing I want to do is I want to look more closely at two rational functions that we studied in our toolkit functions. So let's look at the reciprocal and reciprocal squared functions. So remember, reciprocal, that was f of x is equal to 1 over x. And then reciprocal squared was f of x is equal to 1 over x squared. Okay, so let's look at the reciprocal function first. So this is f of x equals 1 over x. And remember what that looks like, right? So if I draw out a Cartesian coordinate system here. So this is x, this is y, or this is f of x. And remember the function looked like this, right? It kind of blew up to infinity, right, as it approached 0. Then it approached 0 as x approached infinity. And then this side did this. Went down towards the infinity. Okay, so let's talk about the short run behavior of this function. In short run behavior, I mean what happens locally, right? Remember, long run behavior is what happens as the input, the x, gets really, really large or really, really small. Short run behavior is more so what happens locally, right? Usually the intercepts, in this case, there are no intercepts, but we talk about intercepts. In this case, we're also going to talk about something called asymptotes, right? So let's look at the short run behavior here. Okay, so what happens as x approaches 0 from the left? Well, let's look at this picture. So as x gets closer and closer to 0, right, as I approach 0 from the left, what's happening with the function? It's going towards negative infinity. Okay, so as x approaches 0 from the left, our reciprocal function, f of x, is approaching negative infinity. And then as x approaches 0 from the right, let's look at our picture. So as x gets closer and closer to 0, right? So it gets smaller and smaller and smaller, but remains positive. What's happening with the function? Well, it looks like it's blowing up towards positive infinity. Okay, so as x approaches 0 from the right, then the reciprocal function f of x is going towards, it's approaching positive infinity. So the way to write that in sort of more efficient notation is the following. I can say as x, the arrow means approaches 0, and from the left, I just put a little negative on top. So that means 0 from the left. Then f of x approaches negative infinity. And then as x approaches 0 from the right, and you can guess it's going to be a little plus, then f of x approaches positive infinity. Now, in this case, that vertical line, so if I look at the graph again, the vertical line, which is really the y-axis in this case, which has the equation x equals 0, that's what's called a vertical asymptote. So this line, which goes right through 0, it's really the same as the y-axis in this case. This is called a vertical asymptote. And the equation of that line is, remember, a vertical line always has the equation x equals a constant. In this case, it'd be x equals 0. Okay. What about long run behavior? Okay, so we just talked about short run behavior, like locally what's happening. What about long run behavior? What happens as x, the input gets really, really small or really, really large? So long run behavior. Well, I can look at the two cases, right? Let's say x is getting really, really small. So as x approaches negative infinity, what's happening with the function? What is it approaching? Well, let's go back to the function. So as x gets really, really, really small, so as it approaches negative infinity, that function is getting closer and closer to 0, right? It never exactly reaches 0, but it's getting closer and closer to 0 from the negative side, but it's still getting closer and closer to 0. So we can say that as x approaches negative infinity, the function itself is approaching 0. And then as x approaches positive infinity, so now we look over here, as the input gets larger and larger and larger, what's happening to the function? Again, it's approaching 0 from the positive end, but it's still approaching 0. So f of x is also approaching 0. So in this case, the horizontal line which has the equation, you can either write it as f of x equals 0 or y equals 0. That line, which is really the x-axis in this case, that is called a horizontal asymptote. So it is a horizontal asymptote. So let me do that in the picture here. So, oops. So this horizontal line, which in this case is really just the x-axis, that is, it has the equation y equals 0, and it's a horizontal asymptote. Okay, great. What about the reciprocal squared function? Okay, so the reciprocal squared function, remember that's just f of x. Oops, let me go back to black here. So that's f of x is equal to 1 over x squared. And remember, that looks like this. So here's my Cartesian coordinate system, right, x, f of x. And in this case, right, it looks something like this. At least this is the general shape of it. Okay, so let's look at short run and long run behavior. So short run behavior. As x approaches 0 from the left, what's happening with the reciprocal squared function? Well, if you look at this closely, right, as x gets closer and closer to 0 from the left, right? So -1, -0.5, -100th, -1/1,000, -1/1,000,000, etc. What's happening with the function? It's growing towards negative infinity. Or sorry, it's growing towards positive infinity, right? It's getting larger and larger and larger. So this is just infinity. And then as x approaches 0 from the right, so in this direction, the function is also going towards positive infinity. So as x approaches 0 from the left, the function is going towards infinity, and as x approaches 0 from the right, the function is also going towards infinity. So what does that mean? It means I have a vertical asymptote again. At x equals 0. Okay, now long run behavior. So that was short run behavior. So now long run behavior. So as x approaches negative infinity, so as the input gets smaller and smaller and smaller, what happens with the function? And then as x approaches positive infinity, so as the input gets larger and larger and larger, what happens to the function? Well, in this case, if you look carefully at this, the function is again approaching 0, right? 0 from above, but it's still approaching 0. So what does that mean in terms of asymptotes? Well, it means we have a horizontal asymptote at y equals 0, or f of x equals 0. I'll just say y equals 0. Okay, so let me explain this in general. Actually, I'll do a new page here. Okay, so in general, a vertical asymptote of a graph is a vertical line Remember, vertical lines always have the equation x equals a constant, so we'll just say x equals a, where the graph tends towards positive or negative infinity as the inputs approach a. So where the graph tends toward positive or negative infinity, as the input approaches a. So if that happens, right, as you get closer and closer to A, if the graph blows up towards positive infinity, or it gets really, really small and goes towards negative infinity, then you have a vertical asymptote. And the equation of that vertical line is x equals A. Okay, another way we can say that is, so if, I'll write it this way, if x approaches a from the left, and f of x approaches either infinity or minus infinity, so I'll just write it that way, or as x approaches a from the right, and you also have the function approaching either positive or infinity, then there's a vertical asymptote at x equals a. Okay, and then for horizontal asymptote, so a horizontal asymptote of a graph is a horizontal line and remember, the equation of a horizontal line always has the form y equals a constant. Usually we say y equals b, where the graph approaches the line as the inputs get large. So as the inputs get large, and what I mean by large in this case is either large positive or large negative. So another way of saying this is if x approaches, say, negative infinity, and f of x approaches some constant value b, or as x approaches positive infinity and the function is approaching some constant value b, then that means there must be a horizontal asymptote of y equals b. Then you would have a horizontal asymptote at y equals b. Okay, so here's an example. Let's say, let me go to a new page. Let's say we want to sketch a graph of the reciprocal function, but it's transformed. So sketch a graph of the reciprocal function and let's say it's shifted 2 units to the right so shifted 2 units to the right and down 1 unit. And then once we do that, we want to identify the horizontal and vertical asymptotes. Okay, so the original reciprocal function looks like this. I'll just call it y. So y equals 1 over x. So it does something like this, right? It's going to do that. And then, oops, erase this. Wasn't very good. and then something like that. Okay, so shifted 2 units to the right. Let's do that first. So we'll do the horizontal transformations first. So we have a shift 2 units to the right. So what that means now, let's make more room over here. Instead of my vertical asymptote being at x equals 0, right, being the y-axis, I'm going to shift it to the right by 2 units. So the function will now look like this, right? And actually the equation of this function now, call it y1. Well, remember, if I shift 2 units to the right, that means I have to go to where I have x and subtract 2. So that would be the equation, right, of that function shifted 2 units to the right. And then finally, I want to shift it down 1 unit. So now I want to shift down by 1 unit. So what does that look like? Well, it's going to be the previous graph, except now I have to shift it down by 1 unit. So I guess now it's going to look something like this, right? So this is x, this is our f of x, and it's going to look like this. So something like that. So now the actual equation, right, is, well, I previously had 1 over x minus 2, right? That was shifted to the right by 2. And then how do I shift down by 1? Well, remember, you have to subtract 1 from the entire function. So then I would do minus 1. And then it shifted down by 1 unit. Okay. And actually, we can see from the picture, right, what the horizontal and vertical asymptotes are. So if you look at this picture, then we can see we have a horizontal asymptote at y equals -1. And we have a vertical asymptote remember, a horizontal asymptote is if the input gets really, really large, so as x gets really, really large or really, really small, is the function approaching some value? Yeah, in both cases, right? As x gets really, really large, the function is getting closer and closer and closer to -1. Or as the input gets really, really small, so if we go in this direction, small, again, the function is getting closer and closer and closer to -1. So y equals -1 is the horizontal asymptote. And then for the vertical asymptote, the way we figured out is if we approach some value, in this case 2, right? In general it's a, but in this case it's 2. So as x gets closer and closer to 2 from the left or from the right, the function is blowing up. It's either going to, if I get closer and closer to 2 from the left, then the function is going towards -infinity. As I get closer and closer to 2 from the right, the function is going towards +infinity. So I must have a vertical asymptote at the line x equals 2. Okay, and again, we got that just from that picture. All right, now there's one other thing you might want to do with this function. We may want to rewrite it to get, so this is really a rational function, but we want to write it sort of so it has the more general form of rational function. So let's do that. So we found that that last graph, right, had the equation f of x was equal to 1 over x minus 2 minus 1. Okay, let's rewrite this so that we get a better form, or sort of a more general form, for the rational function. So we can actually subtract these two terms, right? You can think of this as a fraction. Here, let me do it one step down. I can think of 1 as 1 over 1. And if I want to subtract these two terms, I have to have the same denominator. I need the lowest common denominator, which in this case is x minus 2. So if I multiply the second term by x minus 2 over x minus 2, then that will allow me to rewrite that second term, and then I can subtract the fractions. Okay, so, well, if you think about this, right, this is going to be 1 over x minus 2. And then I'll rewrite this as a plus, and then negative 1. I have to distribute that negative 1 into the x minus 2. And I have my x minus 2 on the bottom. So this is going to be 1 over x minus 2 plus, and then if I distribute this, right, this is going to be negative x, and then I guess plus 2 over x minus 2. So now we can simplify this, right? We can put everything together in a numerator. I have 1 minus x plus 2 all over x minus 2. So then the final result I can write this way. I can do one more thing in the numerator. I can combine like terms. So I'm going to write this as negative x plus 3 over x minus 2. And again, it's the same exact, this is exactly the same as the original function, right? They're the same exact function. I just rearranged algebraically. But the second form is sort of a more general form of a rational function. So let me write that here. I'll say it's more general form of a rational function. Typically, a rational function you think of as a polynomial in the numerator divided by a polynomial in the denominator. And that's the form we have there, right? We have a polynomial, actually happens to be just a linear function in the numerator and a linear function in the denominator, but linear functions are polynomials. Okay, so let me explain this more generally. So rational functions. So a rational function is a function that can be written as the ratio of two polynomials. So is a function that can be written as the ratio of two polynomials. And usually we call those polynomials p and q, but they can be anything. So I'll stay with that convention. So p of x and q of x. Let's say those are our two polynomials. So in other words, I can write a rational function like this. F of x equals p of x divided by q of x, where these are just polynomials. So I could write this as, let me do it as the most general way possible. I'll say an x to the n plus a n minus 1 x to the n minus 1 plus dot dot dot, all the way down to, I'll do it as a2x squared plus a1x plus a constant over, and then I have another polynomial, but so since it's different, I'll use a different letter to represent the coefficient. So let's say b, so over b and x to the n plus b n minus 1 x to the n minus 1 plus dot 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 b sub 2x squared plus b sub 1 x plus b sub 0. So again, all we're saying is that a rational function is a polynomial divided by a polynomial. Okay, so what about, so how do we investigate short-run behavior of rational functions? So investigating, we'll start with short-run behavior. Investigating short-run behavior. So what does that mean? It basically means finding asymptotes, right? Vertical and horizontal asymptotes and intercepts. That would be the localized, right, short-run behavior. So it basically means finding asymptotes and then vertical and horizontal intercepts. Okay, so let's talk about vertical asymptotes first. So to determine, this is for rational functions, to determine vertical asymptotes, we determine where the function is undefined. Or another way of saying that, remember, our function is undefined when the denominator of the function is equal to 0. So basically, we're determining where the denominator of that rational function is equal to 0. But we have to be a little careful. And where the numerator and where the numerator is not 0. So it turns out if both the numerator and denominator are 0 for some particular input, then we have what's called a hole at that location. Like it's undefined because the denominator would actually be 0, but it's not really a vertical asymptote because the numerator would also be 0, and those two factors would cancel. So in all, this won't make complete sense right now. It'll make more sense when we do an example with this. So let me just write now that a hole might occur in the graph of a rational function if an input causes both the numerator and denominator to be 0. So if an input causes both the numerator and denominator to be 0. Okay, so I think that's actually going to be a good place to stop with part A. And again, this is a long section, so I'm going to do at least one other part. Maybe I may even have parts B and C, we'll see. But I'll stop here for part A, and I'll continue with an example where we find the vertical asymptotes of a rational function. Great, thanks.